Welcome to Summarize Science. Training AI in the real world, like for robotics or healthcare, is incredibly difficult for two main reasons. First, letting an AI learn from scratch through trial and error is risky and can damage expensive hardware. Second, it's often impossible to write a perfect reward function to tell the AI exactly what to do. This paper proposes a clever two-stage solution that addresses both problems at once. First, the AI learns a safe starting policy by simply watching a reward-free dataset of an expert performing the task. This is like an apprentice learning the basics by observing a master craftsman. However, just watching isn't always enough, as the AI might not know how to handle situations it hasn't seen before. That's where the second stage comes in, fine-tuning with preference-based feedback. Instead of writing complex code, a human simply looks at two attempts by the AI and indicates which one was better. The researchers introduce a new unified algorithm called Bridge, which stands for Bounded Regret with Imitation Data and Guided Exploration. It's designed to seamlessly integrate the signals from both the initial expert demonstrations and the ongoing human feedback. This diagram gives a great overview of the process. The algorithm starts with a massive space of possible policies, and the offline expert data allows it to create a much smaller, high-confidence search space that likely contains the best strategy. Then, during the online learning phase, it uses human preferences to explore within the safe, constrained area to find the optimal policy. While this watch-then-refine approach has been used successfully in practice, this paper provides the first principled theoretical analysis of why it works. They derive mathematical bounds which prove that the more offline expert demonstrations the AI sees, the less online human feedback it needs to achieve a great result. Essentially, the offline data dramatically improves the online learning efficiency. To validate their theory, the team tested Bridge in several simulated environments, including discrete tasks and more complex continuous control tasks like the Reacher arm and the Ant robot. They compared its performance against both standalone behavioral cloning and purely online preference-based learning. The results speak for themselves. Across all four environments, the purple line, representing Bridge, achieves a significantly lower cumulative regret. This means it learns the optimal behavior faster and with far fewer mistakes than the other methods. These graphs also show that Bridge rapidly refines its policy search space, quickly zeroing in on the best strategies compared to the baseline, which explores more broadly and less efficiently. So let's recap the key takeaways. This research introduces Bridge, an algorithm that effectively combines learning from expert examples with simple preference feedback. Crucially, it provides the first theoretical proof that this hybrid approach is highly sample efficient, formally connecting the amount of offline data to the speed of online learning. The implications for the future are huge. This work opens the door for developing interactive learning systems that can be safely and efficiently trained by domain experts who aren't programmers. Imagine a surgeon teaching a robotic arm or a factory worker fine-tuning a logistics bot, all by providing simple, "this is better than that" feedback, making advanced AI safer and more accessible for everyone.